Hello everyone, I'm Quentin. I, along with my friend Niraj, worked on object position estimation with MATLAB. Our goal is to estimate distance d in the setup shown here. Both A and B are our camera, and center of the black circle is the object. The whole video is divided into 3 parts. The first one is the setup and collection of data presented by me. The second one is the measuring the performance, and the third is the result and plot presented both by Niraj. I will explain first part, setup and collection of data. As shown in this figure, we draw a rectangle of 80 centimeters by 30 centimeters on a surface of a table. Length is divided into 8 slots of 10 centimeters each, and width is divided into 6 slots of 5 centimeters each. The dimension of rectangle is adjusted according to table surface size. We use 2 cameras as specified in the problem statement. If length of the rectangle is x-axis and width is y-axis, then in this context, right camera is placed on 0, 0 and the left camera is placed on 0, 30, as shown in the figure. Both cameras are parallel to each other. The target is black circle with 5 centimeters diameter. The experimented with circle of size smaller and bigger than 5 centimeters. We found that the circle with size less than 5 centimeters are difficult to detect using MATLAB, and circle with bigger than 5 centimeters go outside the frame. We made sure that the height of camera lenses from table surface is exactly the same as the height of the center of cycle from table surface, so that the center of the circle will always show the horizontal central line of the frame. This is to have convenient detecting circle. Along with camera stand, the height of camera lenses is 30.5 centimeters. Hence, center of the cycle is also the same. We had many options to choose between resolution of the video frame. The video resolution with maximum number of pixels on left of the frame is ideal for this project. Meanwhile, video resolution between 4K and Full HD 1920 by 1080 cannot be used because it will take a lot of to process. Also, MATLAB won't bigger frame properly, hence difficult to visualize. So we choose 1080 by 720 pixel frame correctly, hence easily to visualize. The main issue we deal with, biggest challenge, is recording video by synchronization. Starting both videos at the same time was a tedious task. We did not have a synchronous camera. Hence we use a timer on the cell phone and place it in the corner of the frame. Later we edit the video using timer value as reference. We record this video in 3 parts. The first part was the 8 calibration reading. The second part has 24 sequential reading, and the third part has 30 random reading.
Hello, my name is Neeraj. I will explain implementation and results of the experiment. Implementation consists of 4 parts: goal, calibration, method of implementation, and encoding. I will explain them one by one. First, let us understand the goal of this project. There are 2 cameras at point A and point B. Point E is the target which is a black circle on white paper. The goal is to find distance d such that line EC is perpendicular to line AB. Distance d can be calculated by knowing either alpha or beta. Distance d is length AC multiplied by tangent of alpha. Also distance d is length BC multiplied by tangent of beta. Let's see how we calibrated the setup. Total 8 positions were selected for calibration. They are indicated by blue dot in diagram. Unfortunately, due to camera hardware limitations, many positions, especially between 0 to 40 cm distances, were out of frame from either of the camera. Point 80,0 and point 80,30 are extreme endpoints of 80 cm line. The total distance between these 2 points is 30 cm. Same for 60 cm line. The distance between 60,0 and 60,30 is 30 cm. Points 50,15, 60,15, 70,15 and 80,15 are center points of 50 cm, 60 cm, 70 cm and 80 cm lines respectively. Now we will see how references are noted down and the method used to find the position of the target. Consider line with endpoints 80,0 and 80,30. In setup, they are here. Now consider red rectangle as frame of left camera and green rectangle as frame of right camera. Circles shown in grey color are reference positions of the target. Circle in black is current position of the target. We are considering 80 cm line only. Seen from the left camera, at position 80,30, the target will appear exactly at the center of the frame, and at position 80,0, the target will appear at the rightmost end of the frame. Similarly, seen from the right camera, at position 80,0, the target will appear exactly at the center of the frame, and at position 80,30, the target will appear at leftmost end of the frame. We found that at 80 cm distance, 2 reference positions are 460 pixels apart. Also on table, 2 reference positions are 30 cm apart. So length AB is already known, it is 30 cm. In the left frame, if the target E is at position 80,30, then in this case alpha is 90 degree and beta is tan inverse of 80 over 30, which is 69.44 degree. Similarly, in the right frame, if the target E is at position 80,0, then in this case alpha is tan inverse of 80 over 30, which is 69.44 degree and beta is 90 degrees. These values are saved as reference values during calibration. If target is in between these 2 reference points, then figuring out how many pixels the target is away from reference positions will give the values of angle alpha, angle beta, length AC and length BC. Apparently, distance D can be estimated. This is for 80 cm line. Same can be followed for 60 cm line. And knowing other reference positions from calibration value, any distance D at any position on the table can be estimated. This is the flowchart of the algorithm. Program starts by loading both the videos. Then it extracts one frame from the left video. That frame is a picture. Then it finds black circle in the frame, which is our target, and marks the circumference of the circle by colored ring. After that, it notes down x coordinate and y coordinate of the center of the circle in pixel values. These x and y coordinates are compared with the reference positions from calibrated data. With the comparison, values of angle alpha, angle beta, length AC and length BC are calculated. After that, distance D is calculated with the help of alpha, beta, length AC and length BC. Finally, the distance D is encoded with maximum of 2 bits for each frame. The process is carried out for next frame until all the frames in the video are processed. This algorithm is applied to left video and right video separately. The final distance estimation values are the average taken from left and right videos. The final task given is that for each frame produce one bit of information to estimate the position of the black circle as frames pass. But in our observation, as frame pass, estimated distance d of the target can increase, decrease or remain same. So there are three possibilities. Hence, one bit for every frame is not possible. Hence, we assign maximum 2 bits per frame. We observed during implementation that the state of no change in distance occurs more than 50% of the time. Hence, code 1 for no change in distance, code 01 for increase in distance, and code 00 for decrease in distance. The codes are prefix-free codes. There are two assumptions for encoding distance values. From frame to frame, distance value increase or decrease only by 1 centimeter. If increase or decrease is more than 1 centimeter, then definitely more bits are needed to encode that information. Fortunately, in our observation, distance d never changes in step size of more than 1. Though our algorithm is able to estimate distance with 1 decimal digit accuracy, while encoding, only integer value of the estimated distance is encoded. For example, 76.4 centimeter is considered 76 centimeters and 76.56 is considered 77 centimeter. The example of encoding is shown here. Considering initial distance equal to 80 centimeter, hence first value 80 is encoded as 1, which indicates no change in the distance. Second distance 80 centimeter is also encoded 1. Third distance value 79 centimeter is encoded as 00, which indicates decrease in distance. The fourth value 78 is also encoded 00, which indicates decrease in distance, and the process continues as the frames are received. Now we will see results and plots. There are 4 parts: sequential readings, random readings, results and plots. I will explain them one by one. In sequential readings, there are a total 24 readings taken in sequential way. All the readings positions are indicated by blue dots. 7 readings on 80 centimeter line, 7 readings on 70 centimeter line, 7 readings on 60 centimeter line and 3 readings on 50 centimeter line. All the other readings are out of frame from either of the two cameras. We will see how algorithm works for sequential reading. There are total 2728 frames of sequential readings, starting from frame number 1672 to the frame number 4400. As you can see, estimated distance for each frame is encoded as frames are received. In random readings, there are total 13 readings taken in random way. All the reading positions are indicated by blue dot. We will see how algorithm works for random readings. There are total 1917 frames of random readings, starting from frame number 4601 to the frame number 6518. As you can see, estimated distance of each frame is encoded as frames are received. Let's see results. Here are observations of sequential readings and random readings. All the distances are in centimeters. Here it can be seen that original distances and estimated distances are almost same. Let us see plots. Here are the plots of sequential reading and random readings. On the x-axis there is reading number and on the y-axis there is a distance. It can be seen that original distance curve indicated in blue and estimated distance curve indicated in orange follow each other pretty closely.